Hello once again. This is the monthly edition of TEK Talk. This is Mary Angela Tuck recording live from our home studio here at Wheelchair, United Kingdom. Well, we're very fortunate because our guest for today is a very busy person. He works at HEL Group based in London. We met him at the Silverstone Battery Tech Expo. Well, Silverstone is in England, as you all know. He is an application leader and a very able person to speak about the topic that they agreed to speak about today. Well, our mainstay guest is from New York. He's Alex Kosyakov. He is a very young president and founder of Natrion. The company is very promising as it accomplished numerous things in the field of solid state battery. He'll be introducing more or speaking more about himself later. Okay, and introducing our host, Dr. Jonathan Tuck. Dr. Jonathan is a scientist. He is a holistic energy expert and a book author of A Theory of Everything, things I wish I'd known at your age. There you go. Okay, so now I'm going to leave the three of them. They're more of the science and the techie guys. I'm not. I'm just here to introduce them. So, yes. All right. So let's start with, okay, John, take it away.
Well, I think if Alex introduces himself, then I can introduce Mario. Thank you.
Yeah, thank you, Angela and John. Great to be back on Tech Talk. I'm Alex, co-founder and CEO at Natrion. As Angela mentioned, we're a solid-state battery technology startup based in the US with locations near Chicago and New York. And we're developing advanced rechargeable batteries primarily for electric vehicles, consumer electronics, all sorts of different applications. We've been around for about 5 years now. Still kind of a small team. We're at 18 people, but we've been moving along and working with some of the biggest automakers and consumer electronics manufacturers in the world. So, yeah, very excited to speak with Mario today and be back on Tech Talk.
Awesome, thanks, Alex. Yeah, I mean, as Angela introduced, I'm John Tuck. I'm a holistic energy scientist, and I'm representing my company, Silent Koala, today. As I've mentioned previously, I've got quite a bit of experience in the energy storage and even generation arena. I started working in fuel cells in 2001. I co-founded a supercapacitor company in 2014, and I currently work for the last 5 years with a UK battery manufacturer in intellectual property and innovation, which has really given me the opportunity to explore the plethora of chemistries and formats and sort of cutting edge and blue sky levels, which has been very interesting for me. Now, we've had a variety of different guests from different areas of the industry, each of whom have provided a fresh perspective on the global situation and how they see it. So it's great to have Mario with us today, as I can see that the testing arena and testing equipment arena is actually a good platform or good position to be in to give us a good perspective on what's going on in the background from a more cutting edge and blue sky perspective. So it's my pleasure to introduce today Mario Tilbis from HEL Instruments. Mario, if you'd like to just introduce yourself and we can take it from there. Thanks.
Yeah, sure. So, well, first of all, thank you very much for having me. As John has said, my name is Mario Tilbis Rodrigo, and I am the applications leader at HEL, but I have quite an interesting background. So my role nowadays basically consists of talking about what my company does. So HEL works in a number of different fields. We have battery testing, as you have mentioned, but we also have bioreactors, we have chemical safety and process scale-up. The way that I landed on this position was quite a journey. My background is in biotechnology. And after that, I quickly moved away from that field because I felt at that time in my life, I was like, maybe this is not the right fit. So I decided to go more into basic science. So I spent 3 years doing my PhD trying to find what kind of microbes live in underneath glaciers in Iceland. And then I moved from there into astrobiology, trying to find what kind of microbes potentially could live on Mars. But then I realized that what I have enjoyed the most in all this journey was just talking, writing about science. So at that point, like I would say 8 months ago, I decided to just quit academia and get more into the science communication world. And this is how I ended up working at HEL. So yeah, that's very much me. I could say, I jokingly say that I am basically a science bard.
No, thank you, Mary. That's fantastic, and I can kind of relate to that because my career has taken a very diverse path, and what I realized was that most of what I've done in my life has always been energy centric. So from quantum physics through chemistry, electrochemistry, even towards biology, and I'm fascinated with what you do. Biology is one of the reasons I call myself a holistic energy scientist is because I understand energy from first principles across the range of sciences. But biology is my weakest. That's where I'm really learning at the moment. So I'm sure we can have a chat offline about.
Oh, absolutely. Absolutely. Because at the end of the day, energy is in everywhere. Life is no exception.
Absolutely. You know, if people used to ask me what I was into, I'd say everything.
I mean, you have a book that's the theory of everything that shows it.
Absolutely. My grounding behind that is that everything, fundamentally what I'm into is energy. And since everything is energy, it makes sense.
Absolutely.
Anyway, we digress. Let's have a chat with Alex. What sort of questions do you have for Alex? I mean, the whole solid state arena is an absolutely fascinating arena. So go ahead, ask Alex.
Yeah, absolutely. So as I mentioned, one of the things that the HEL manufactures is battery testing, and obviously one nowadays only has to look into the news, and we can see that there is so many fires that are linked to lithium-ion batteries. So obviously it seems that solid state batteries is the future here. So I would like to ask Alex, for someone who's just got into batteries and still trying to come to grapple with it, how would you explain what a solid state battery is?
Yeah, sure. Yeah, I mean, most if not all consumer electronics right now, and then most electric vehicle models are using these lithium-ion batteries, which have been a mainstay technology for over 30 years now. And yeah, solid-state battery is basically a lithium-ion battery, except you're trying to reduce or eliminate the liquid components inside of the battery cell. So these lithium-ion batteries right now are made with a liquid electrolyte. This is the charge transferring component inside the cell. And it's literally a liquid, and it's comprised of all these very volatile hydrocarbons, and you're combining that with really oxidizing lithium salts. And so fuel and an oxidizer, and there you go. That's where all the flammability comes from in a lithium-ion battery. But it's also the source of all our performance bottlenecks with lithium ion right now. So you can't charge quickly because fast charging means putting a lot of current through the battery, and a lot of current is just going to cause your liquid electrolyte to fall apart and decompose into combustible products. Similarly, we can't push current lithium ion batteries to high voltages, or at least really ink out the coax the most energy out of these cells that we could, again, because we would, the liquid electrolyte wouldn't like it. So, switching from liquid state materials to solid state materials to transfer charge inside the battery can substantially improve safety and performance, albeit if you do it right. So I think, the challenge right now is that most people have found that really the holy grail is what's called an all solid state battery, where the whole battery cell is just solid materials, but that's been very difficult to try to scale and commercialize. And so most approaches right now that have seen some commercial success are more hybrid approaches where we're striking some kind of balance between the amount of liquid and solid in the battery. Maybe it's not all solid state, but at least by replacing some or most of the liquid, we could still realize some of these safety and performance benefits. So, and the implications can definitely be, extremely beneficial for the automotive industry and all sorts of other areas of electrification. And that's why people are really excited about this technology, and that it's really going to be the first big step that we take away from lithium ion in the last 30 years. So
I think that one of the things I found the most fascinating when I first got into this field, and I was actually doing some research on lithium-ion batteries, was the fact that you basically have the three pillars of a fire on a battery. Because obviously, the first thing you have is, as you mentioned, the electrolyte that when exposed to high temperatures, especially if you have runaway events, is going to decompose. As you said, it's going to generate all these potential volatiles that are highly flammable, such as, I don't know, ethane, propane, that are used as biogas. And then you have the oxidizers, and at high temperature as well, if you have especially oxides, like cobalt oxide is going to generate oxygen. So you have the fuel, you have the oxygen, and you have the energy. So I think that this is where HL, for example, does a very good job, because we are actually devoting a lot of our efforts into trying to increase the capacity of testing for batteries, especially for lithium-ion batteries. So what do you think that the future of battery testing is going to be? And how do you think companies like the one I work for are going to be moving towards?
yes, I think we're still learning a lot about how batteries need to be tested. I mean, even like you're just starting to see now legislation kind of around the world catch up, and people are realizing we're putting these lithium-ion batteries and everything. And at least I know here in the US, New York City has had an immense problem with electric scooters and those catching fire and causing building fires that have been, ended pretty catastrophically. And so New York City has just started to realize that, hey, these batteries need to be tested, and there need to be some kind of standards that they need to meet. It's tough because it's a balance of people really wanting to, put out new chemistries and new battery devices. At the same time, you gotta push back on that and make sure these devices are safe. Now, from a testing point of view, and this is starting, I think the big challenge in the battery industry is how do you determine and learn as much about a chemistry as you can in a way that's non-destructive. And so, and that applies to all sorts of different electrochemical and instability tests, but doing so in a non-destructive way seems to be kind of a focus in metrology and, overall and in space. And so there are all these kinds of interesting things starting to crop up, like, people using ultrasonic to probe kind of a battery cell and try to use something like that to search for short circuits inside of a cell before that cell has even gone out to market.
Yeah.
Because it's short. There's very few things more dangerous than a short circuit lithium-ion battery. So that's the direction we've seen things moving in, and really a lot of exciting innovation happening and more to be done.
Yeah, but when you were talking about ultrasound for battery testing, that's definitely a destructive method. It's not a non-destructive. Basically, you're forcing the short circuit into the battery, aren't you?
Yeah, no, I guess it depends. But well, you're the expert, so.
Yeah, no, because I was more thinking on strategies that involve calorimetry, like isothermal calorimetry, to try to just increase the temperature, maintain it, to try to find and search where the runaway event is going to happen. But yeah, definitely ultrasound is something that I've never thought of at the time of battery testing, and that is something that definitely I really want to check on. So I guess I have another question for you, and because obviously you are the expert on solid state batteries. So if when we have liquid batteries with electrolytes, obviously it's organic carbonates that are going to potentially decompose. What kind of materials are used for solid state? Things such as semiconductors, or what kind of material is it?
Yeah, I think broadly speaking, there are kind of two main flavors of solid state electrolytes. There's the organic polymers and inorganic ceramics. And so what I think the kind of the prevailing approach has been the inorganic materials, because you can get really fast high throughput ion transport in certain inorganic materials. And so there are ceramics like lithium lanthanide zirconate, LLZO. This is an oxide type ceramic, or there's a whole set of sulfide ceramics that show fast ion transport, and people have been really excited about these materials now that the challenges with those kinds of ceramics is more of the processability and their mechanical properties. So it's very difficult to make ceramics into thin films, but that's kind of what you need to produce efficient battery cells.
To then bend them around a cylindrical cell construct. Yeah.
Exactly. Yeah, and not to mention that sulfide is unstable in air, and LLZO, for example, also unstable in air. So they're really tough to handle and process, and require things like high temperature calcination and all these exotic processes. So that's been the challenge with those. Now polymers are really easy to from the standpoint of making them into robust thin films with great mechanical properties, except that polymers aren't so good at moving ions quickly. And then there's kind of a third class of these solid electrolytes where you have some kind of combination of polymer and ceramic, and that's what we do at Natrion. Is we deal with these hybrid or composite type solid electrolyte systems where we try to kind of leverage the great mechanical attributes of a polymer and the fast ion transport of a ceramic.
That is very, very interesting. You mentioned sulfide ceramics.
Yeah.
Do they decompose to generate like sulfide, like sulfides, like hydrogen sulfide, or not?
No, I mean that's not so much the problem as that they need to be made with hydrogen sulfide. So
okay, yeah, that was what I was thinking. When you have sulfides, it's like there's going to be a hydrogen sulfide somewhere.
Yeah, they're just nasty materials, and we actually, back when we were starting out, we did investigate sulfides. I think one of the major motivations that we stopped working on it for stopping working on it was that it just the lab smelled awful.
Well, if that helps, I spent so my postdoc was 5 years, and I was working on these sulfate-rich lakes. And some of the microbes that I was cultivating, what it did was just reducing the sulfide into sulfide. So every time that I had to do any kind of experiment, everyone in the lab just ran away from me, because that was just one of the things. But I got like somehow the nickname of the smelly one, because it was, in one hand, it was the sulfate reducers, but also some other of the micros I was working with, they reduce trimethylamine. And trimethylamine smells like rotten fish. And then I also, some of the other micros that I was working with, they have the ability to oxidize butyrate, and butyrate smells like smelly feed. So trust me, every time I just walked into that lab, everyone's like, why are you here? Why are you doing this to me?
That's very funny, Mario. Yeah. Yeah.
So yeah.
Yeah, no, thank you. One of the things I'm really curious about from you, Mario, is whether you've any insights into what else is going on from a grassroots perspective in terms of who you're supplying equipment to, and if you're able to tell us. If you're not able to tell us, we absolutely understand. But if you're able to give some sort of insight into what people are working on, or sort of generically where you see the industry is going.
So I can see that in the time I've been working with HL, definitely there is a push trying to get safer batteries, because as Alex was saying about New York and the fire links to lithium-ion batteries, we are seeing the same in London. I was doing some research for a blog post that we had some months ago, and just between 2021 and 2022, the amount of fires linked to scooters and e-bikes here in London increased something like 23%. So that is huge. And some more of the research that I did into this, I found this report by Zurich Insurance, and they have found that if you go online and you try to buy for e-scooters and e-bikes, something like 20-something of the most common visited listings actually have unsafe batteries. They were lacking some of the basics, such as fuses, in case there was some kind of short circuit. So I can see that the battery community is definitely moving towards trying to correct this problem, because obviously the main problem is not only that it's putting people's lives in danger, but also these damages the reputation of the manufacturers, and it can also incur into criminal offenses and definitely very, very big fines. So I can really see that the battery industry is moving towards trying to reinforce the safety in batteries. And then, as Alex said before, finally, it seems that governments are trying to gear towards having some kind of legislation that is going to ensure that the batteries that are being sold and manufactured are safer to prevent further problems.
Yeah, no, absolutely, Mario. I think it's, I think we shouldn't detract from the fact that historically, once lithium-ion batteries have been developed, then they were very safe. As much as the danger presented, the way they were packaged and developed and then subsequently tested and more tested, made them ultimately very safe.
Mm-hmm.
Although you still, or at least 5 years ago, 10 years ago, you could be prevented from taking your phone onto a plane if you couldn't boot it up.
Yeah.
And that is because the cells themselves become unstable under a certain charge percentage or voltage.
Yeah.
So measures were in place, but
yeah, what was it was Samsung Galaxies that studied all this problem in planes. And again, these links, as you said, to the instability of some of the batteries, they can just get into runaway and just get into this huge increase in temperature that just results on a fire. And obviously, it is dangerous enough as it is if it happens in a house. But imagine if you are flying at many thousand meters over sea level and you're basically in a frying can and you have a fire starting. So, and it is fascinating. What I found the most fascinating is basically it's the same problem that we can see nowadays. It's just that obviously, first of all, it was phones. And now with e-scooters and e-bikes, is that you are packing more energy, you're packing a higher density cell in it. So it's just a matter of, yeah, but lithium-ion batteries are not unsafe per se. It's just the way that they are treated and the way that they are exposed.
You touch upon a significant point. I mean, in battery cells, there's two significant parameters. One is the energy density, which is what conventional lithium-ion batteries are focused on. The other, which is the holy grail now, and which Alex alluded to, is the power density. So the energy density, the amount you can get into the vessel, but the power density, the rate at which you can get it in and out.
Yeah.
And that's when you come up against the challenges of safety and instability of the current, particularly electrolyte solutions.
Yeah.
Yeah. So yeah, I mean, interesting times. I mean, Alex, do you have any further comments on this?
Yeah, well, so I think we're finally starting to kind of get the data. So there's a lot of kind of different data points that can sometimes tell different stories. So there's a lot of evidence that actually, electric vehicles have a lower propensity to catching fire than normal internal combustion engine vehicles. In other words, the rates of fire are lower. The problem is more that that when an electric vehicle does catch fire, and like Mario said, like there's so much energy in that battery pack. It's unlike any fire that firefighters are used to or trained to handle. These electric vehicles will burn and burn and burn for days. And the only thing you can do is just keep pouring water on it continuously to keep the blaze from damaging surroundings or so forth. So it's more that there's kind of like two components to everything. It's like the probability of risk is really the probability of something happening and then multiplied by the severity of that event occurring.
Yeah.
And with electric vehicles, we're kind of shifting the risk towards severity versus with scooters and electric bikes. It's the thing is that electric vehicles, they have to meet highway traffic safety board regulations or whatever. But some of these scooters, they come from, they're hobbled together in overseas factories or whatever, and most of the time without any regard for, as Mario said, they probably don't have fuses built in or whatever. And so really the only thing you can rely upon is the intrinsic safety of the cells. And I think that's the real opportunity in safety with solid state is you can make a battery cell that's intrinsically perhaps safer, where less of the risk mitigation is now concentrated at the system level as opposed to at the cell level. So shifting the risk mitigation. But yeah, and I'm curious to kind of learn, about maybe some of the things HEL or Mario has seen being developed as far as testing, because it's a whole different thing as far as like how do you construct experiments that'll simulate the duty cycles and the use cases that batteries will face. So I think Mario said, you mentioned calorimetry, and this is where you're externally kind of heating up a battery cell and seeing at what point you trigger the cell to start self-heating, where reactions inside the battery start to make it heat up even faster than its surroundings are heating up, and then it causes that thermal runaway event. Well, it's there's a whole lot of things to consider there, like what is the state of, John, you mentioned state of charge, right? So a fully charged battery cell is a much greater risk of starting self-heating than a depleted cell or a cell at a lower state of charge, and then all sorts of different factors. And so how can we design better experiments and better measurements to actually mimic what batteries will face in the real world That certainly seems to be a major challenge right now.
Yeah, definitely, and actually, I'm glad that you bring that up, because actually that's how HEL started. HEL stands for Hazard Evaluation Laboratory. So
Oh, fantastic! Thank you.
yeah, so
Yeah.
HEL started in the 80s. Actually, HEL is just a bit older than I am. I think that started in 87. I'm from 89. And it started just as like electrical hazard testing. But then quickly, the founder of the company decided to move away just from the testing, because he realized that there was no real good way to measure the hazard as it was at the time. So this is how it just moved away and started designing and developing their own instrumentation. So basically, the way that HEL focuses the battery testing, which we don't do in-house anymore. We just manufacture the instruments. Is basically calorimetry. That's what we're most interested in. So all our equipment for battery testing focus on calorimetry. As you said, you supply certain amount of energy and temperature just to check how the battery reacts to it. And we have developed both for non-destructive and destructive methodologies. So we have we have testing for just as you said, increasing temperature slowly to see how it increases until we can find where the runaway event is. But also we have developed equipment in which you have these huge containers in which you can have the battery, and it's equipped with cameras in order to just use things such as puncturing of the battery to see how it reacts. And as you said, one of the main differences is you have a discharged battery and you puncture it and nothing really happens. It's just going to be like a bit of a pew, and that's it. But if you have a very densely packed battery and you perforate it, the risk of fire is just incredible. So I think that is definitely things that are needed to bear in mind at the time of battery testing. Yes, you can test the battery for processes just charge and discharge and see how the battery reacts, how the battery ages as well. Because obviously subsequent process of charging and discharging are going to result on the battery being less efficient because of the proper aging of the battery. But also you need to evaluate what is the worst case scenario, because you never know what is going to happen to that battery. Maybe you have a perfectly new battery that is going to be in a brand new car, and on your first test run, you're going to end up involved in a traffic accident. And you don't want all that energy that is densely packed inside of the battery to just immediately escape away. And as you said, the actual chance of it is lower than if you have a normal combustion car, but the risks of being involved in this are much higher. So I think just summing up, that both types of testing are incredibly useful techniques that we need to apply for any kind of new battery being developed.
Thanks, Mario. I guess the question goes further to ask: is there anything that you're excuse me, aware of on the horizon in the testing arena that is coming up to improve the quality of the results you get? Have you any inclinations or feelers out on the?
Yeah, I definitely, I know that what companies like ours are doing is just trying to increase our testing capabilities, because obviously as batteries are evolving and becoming more powerful and more densely packed, the current instruments that we have might not be safe enough. So we have to find a way to scale up to make bigger and more powerful testing and more resilient testing instruments in order to be able to cope with the demand for higher energy. Because one only need to get and check on Google what the main trends in batteries are, and it's trying to increase how much energy you can store in a battery. Because
yeah, absolutely.
just think of your phone. I mean, think of Nokia's in the 90s and early noughties. You can have a Nokia running for a week and it was perfectly fine. Nowadays,
Yeah,
more than a day is just red and it happens.
yeah, yeah.
So definitely that's the main issue. Is just we need a more powerful battery, but also we need to at the same time be able to test for safer batteries at the same time. So it is that for me, what I think the trend is trying to harmonize these two fields so they can go on this journey together in order to get safer and healthier and more sustainable batteries.
Very great, thank you. And so are you excited about what Alex is doing now? Can you see how,
Very much,
you know, this
very
is really
much.
very forward-thoughted. I mean, let's not forget, in the bigger picture, driving around on however many gallons of diesel or petrol isn't exactly the safest thing
No,
one
not
could
at all.
imagine either. So, you know, clearly we've been in a position whereby people have been very nervous about having a petrol tank, and then we've developed the solutions synonymously to what Alex is doing for the battery, in order that we could move forwards and everyone could actually be safe.
Yes.
Most of the time, you know.
But also, one of the greatest things about electrical batteries is that the energy that you can use for them can come from renewable sources, making it.
Yeah.
Whereas if you have diesel, if you have gas, it's going to be incredibly polluting and incredibly unsustainable. So we really have to balance these things out at the time of deciding where we want to go and what kind of technologies we want to develop and how we want to develop them.
Yeah. Well, absolutely. Well, that's fantastic. I think we're coming to the end of our allocated session now, but that's been really, really interesting. Thank you so much, Mario. Thank you, Alex. It was great for you to. It's the first time Alex has actually really explained the technology to our audience. So thanks for asking that question, Mario.
You're welcome.
Learned a bit too. So
I mean, for me, it was a great moment because I love learning. So getting to learn about this kind of technology in particular, it is super useful for me as well. So thank you very much, Alex, for explaining that to me.
Yes, no, it was fantastic to get a perspective on what's happening in the testing industry. So thank you very much, Mario. I learned a lot as well.
Thanks, Alex. And we know you're extremely busy fighting your own metaphoric fires with all of the great stuff that you're doing. So yeah, I guess if everybody's happy, we'll leave it at that. And certainly Alex and I will be back for another edition with another guest next month. And yeah, thanks everybody for watching, and thanks to Mario, thanks to Alex.
Thank you very much for having me, Ori.
Yeah, it's been a pleasure.
Thank you all.
Thanks, Mario. Thanks, Alex.
Bye.
Bye.
Are you stop recording now?
I'll just go and tell Angela disappeared. She was doing some prayers or something. I'll just go and tell her, and then we'll have a quick chat before we.
Cool.
We're done.